You know when you open your favorite app and everything just loads instantly? You're pulling data from servers that could be on the other side of the planet, but it all shows up in milliseconds. How on earth is that possible? Well, the answer is a really clever, multi-layered strategy called caching. And today, we're going to break down exactly how it powers pretty much the entire modern internet. Okay, let's get right into it. The speed of light is a hard physical limit. You can't get around it. So, a request from, say, Tokyo to a server in Virginia and back is always going to take time, no matter how fast your fiber optic cable is. That delay, that's latency. So, the only way to beat latency is to kind of cheat distance. And that's exactly what caching does. It brings a copy of the data a whole lot closer to you. To pull this off, modern systems use this whole hierarchy of caches. So in this explainer, we're going to follow a single request as it travels through each layer. We'll start with the cache that's literally inside your own browser. Then we'll move out to the global edge network of CDNs. And finally, we'll hit the application's own super fast in-memory cache. We'll also have to tackle the notoriously difficult problem of cache invalidation before we put it all together. All right, so our journey starts at the closest possible point, your own device. This is the browser cache, and it's a private cache that only you can use. Think of it like this. Instead of running to the library for a textbook every single time you need to study one chapter, you just photocopy the important parts and keep them in your backpack. That is your browser cache. It stores all the static stuff, images, style sheets, JavaScript files, right there on your computer's hard drive. So the very first time you visit a site, your browser sends a standard GET request for, say, a CSS file. The server sends back the file, of course, but it also includes this really important HTTP header, cache control. A little directive in there like max age equals 86400 is the server telling your browser, hey, this file is good for the next 24 hours. Don't even bother asking me for it again. Just use your local copy. So let's see how that plays out. If you visit that site again within the 24-hour window, the browser doesn't even make a network request. It just pulls the file from your disk. We're talking 0 milliseconds of network latency. It's instant. But what happens after 24 hours? Well, now the cache is considered stale. At this point, the browser sends a quick conditional request with something called an E-tag. You can think of it like a version number or a fingerprint for the file. If the file on the server hasn't changed, the server just sends back a tiny 304 not modified response. It doesn't resend the whole file, saving a ton of bandwidth.
Browser caching is fantastic, but it only speeds things up for one person, you. To make a site fast for millions of people all over the world, we need to go up to the next layer, the Content Delivery Network, or CDN.
So what is a CDN? It's basically a massive global network of servers, all placed in strategic spots around the world. The best analogy is a pizza chain. You wouldn't have one giant kitchen in Virginia trying to ship pizzas worldwide, right? No way! You'd open up local shops. That's a CDN. When a user in Berlin requests your site, they don't hit your main server in Virginia, they hit a CDN edge server that's right there in Germany. And we can actually control these shared caches with a slightly different directive. While max age is meant for the private browser cache, there's also smax age. The S stands for shared, and that's for things like CDNs. This gives developers really fine-grained control. You could tell a user's browser to cache a file for just an hour, but tell the global CDN to cache it for a full day. Pretty cool. But this brings up a really important question. How do you cache stuff that isn't the same for everyone? What if you want to show a different version of a page for the same URL based on, say, the user's country? That's where the vary header comes in. It's an instruction that tells the cache, hey, create different versions of this page based on a request header. So by setting vary x versal IP country, the CDN will store and serve a unique version of the page for users in the US, another for Germany, another for Japan, and so on. It makes localized content super fast. Okay, so we've cached our static files close to the user. But what about all the dynamic data, the stuff that lives in a database? To speed that up, we have to turn to our final layer of defense, the application cache. This is where tools like Redis really shine. Redis is an in-memory data store. That means it keeps data in super fast RAM, not on a slower disk. It acts like a high-speed buffer right in front of your main database. If your database is the big, slow walk-in freezer down in the basement, Redis is the prep counter right next to the stove, holding all the ingredients you need right now for instant access. Now, the most common way to use this is a pattern called cache aside. Here's how it works. A request for data comes in.
First, the application checks Redis. If the data's there, boom, that's a cache hit. It's returned immediately. If it's not there, a cache miss, the application has to go query the main database. Then it takes that result, stores it back into Redis with a time to live or TTL, and then returns it to the user. Why? Because the next request for that same data is going to be a cache hit.
And the performance impact here is just staggering. A cache hit from in-memory Redis might take just 2 milliseconds. But a cache miss that has to go all the way to a database, that could be 150 milliseconds or more. We're talking a performance improvement of almost 2 orders of magnitude. At scale, that is absolutely massive. So, caching seems like a total magic bullet for performance, right? But it introduces this huge new challenge. What happens when the original data changes? This brings us to what a lot of engineers consider the hardest problem in all of distributed systems. Yeah, this famous quote from Phil Carlton pretty much says it all. If you get cache invalidation wrong, you end up serving stale, incorrect data to your users, and that can be just catastrophic. So, cache invalidation is just the process of telling all of your caches, the browser, the CDN, the application cache, hey, this piece of data you're holding is now out of date, get rid of it. Think about it. If a user updates their profile picture, but your CDN keeps serving the old one for another hour, you've got a really bad data consistency problem. Generally, there are 3 main ways to handle this. The simplest is just using a time to live, or TTL. You just wait for the cache to expire on its own. It's easy, but it guarantees there'll be a period where your data is stale. A more active approach is event-based purging. When data gets updated in the database, it fires off an event that explicitly tells the caches to delete that old entry. This is way more complex to set up, but it gives you near-instant consistency. And finally, for static assets, the best strategy is called cache busting. You just change the file name. A request for style.v2.css is seen as a totally new file, which completely bypasses any old cached version. Okay, we've looked at all the individual layers. Now let's put it all together and trace a request through the entire system, from start to finish. But first, it's super important to know what can even be cached by a shared system like a CDN. There are rules. The requests have to be a simple GET or HEAD request. It can't contain an authorization header, and the response can't be trying to set a cookie. Basically, these rules are a safety net to prevent personal or private data from ever being accidentally cached and then served to the wrong person. So here it is, the full journey. Your browser first checks its own private cache. If it's a miss, the request goes out to the nearest CDN edge server. If that's a miss, it finally travels to your application server, which then checks its Redis cache. Only if all 3 of those caches miss does the request finally hit the origin database as a last resort. And then, as the response travels all the way back to you, it populates each cache layer it passes through, making it much more likely the next request will be a hit. So, let's recap the whole system. You've got the browser cache, a private copy just for you. Then you've got the global CDN cache, a shared layer that crushes network latency for everyone. And finally, you have the centralized application cache, which acts as a shield for your database. Each layer works together, and each one solves a different performance bottleneck. And that brings us to what is really the golden rule of any high-performance system. The goal is always to cache as aggressively as you possibly can, for as long as you can, but you have to have a really smart, precise strategy for clearing that cache the very instant the underlying data changes. And that leaves us with a fundamental question you always have to ask when you're designing a system like this. Caching gives you this incredible speed and scale, but it forces you to face this constant trade-off between performance and consistency. Your data's fast, sure, but is it correct? The answer to that question really defines the entire architecture of the modern web.